So welcome. Thanks, everybody, for coming out. This is the start of the machine data track here at Strata. And I think this is going to be a very interesting track. I think we have a lot of really very relevant talks about how machine data affects your lives, everybody's lives, energy, transportation, industrial applications, IT infrastructure, data centers. All of these things have this property where they're generating enormous amounts of data, and we want to be using some of these interesting tools and techniques to try to harness and get something interesting out of that. So my name is David Andrzejewski, and I work at Sumo Logic. I have the unique position of being both your track host today for the machine learning track, as well as, or the machine data track rather, as well as the first speaker. So I will get to introduce myself. So this next speaker, he's a great guy. Going to be a great talk. All right, David Andrzejewski, take it away. So, thanks. Like I said, I work at Sumo Logic, and I do data sciences engineering there. And so you'll hear all about the details of that. But first, I just want to say what the talk is about. Machine learning for machine data. And the one takeaway that I'd love you to get here is that machine learning can be awesome applied to machine data. Machine data can be really messy and unruly and kind of out of proportion to human scale, human understanding. And machine learning can kind of help bring it down to a level that actual individual human users can get some insights out of their machine data. So I'm going to try to say what we're going to be talking about, and we're going to be talking about log data specifically. So Sumo Logic is a company that deals with machine log data. So this is basically any machine infrastructure is going to be writing these logs out, kind of saying what it's doing, and Sumo Logic is a service that deals with those, so that's kind of what I've been working on. I'm going to be talking about how you can solve log problems with machine learning, and going through some specific examples, both from within the Sumo Logic product, stuff that we've done that I think is pretty interesting, and stuff that you can do outside of Sumo Logic. I'll also be talking about some particular use cases, why you would be interested in log data and the kind of value you can get out of it. And then also, this is really important, I'm going to try to generalize the stuff we've learned building these features in Sumo Logic to kind of try to back up and extract some general lessons about building tools for machine data and tools that incorporate machine learning. So any communication, talks, blogs, papers, anything is also defined by what it omits, what we're going to leave out. So in this talk, there's not going to be much of a Sumo Logic deep dive. We have a booth in the hall, and people will be happy to talk your ear off about Sumo Logic. There's not going to be much tech stack talk. That's kind of a whole separate conversation. I'm really going to focus on the machine learning stuff. I'm going to not do too much of kind of trying to shock and awe you with numbers about the big data and the machine data and this kind of thing. There'll be very little of it to just kind of try to give you some context, but that's not going to be the focus. There's not going to be a machine learning algorithm shootout. There have been lots of interesting talks at Strata about different algorithms and different approaches. Actually, in this talk, what I'm going to try to do is just show you the machine learning problem. So try to give you crisply defined machine learning problems and how to think about stuff in that way. And particular algorithms can be left to your own devices. That stuff's the fun part often anyway, and people love playing with that. Not any extreme math, unless we get to the very end and I have a little extra time, and then I can get extreme math all over you here. But the context, so my background is, like I said, I do data sciences at Sumo Logic. I'm also the co-organizer of a machine learning meetup in San Francisco. So any machine learning folks who are local or just happen to be visiting, interested in doing a talk, absolutely get in touch with me. Before that, I was doing a postdoc in knowledge discovery at Lawrence Livermore. And way before that, I was doing machine data research projects both at Wisconsin-Madison and Microsoft Research. And so actually, if you were lucky enough to catch Alice Zeng's talk in the hardcore data science track, some of that stuff about why is my computer so slow and how can we figure that out from machine data, I was lucky enough to work on some of that with her. So Sumo Logic. Obviously, this is also going to be kind of relevant to give you some context. And I'm contractually obligated to give you that little tagline right under there. But in a very simplified sense, Sumo Logic is a service that you would send your log data to from anything that writes logs. And it's cloud-based. and then you can use it to do stuff like search your logs, monitor your logs, visualize things, make dashboards, and the fun stuff that I'm going to be talking about, and do machine learning, do prediction, do this kind of advanced analysis on your logs. So there's two sides to the service, and like I said, I'm really not going to talk about the other side at all. I'm going to be talking about this stuff that I'm particularly personally associated with. So log data. What's log data? This right here is an example log from the Sumo Logic service. So we actually do this dog fooding where we run a shadow version of the service that we feed the logs from the production service into. So we can kind of eat our own dog food and play with the service and really learn what works and what doesn't when we're trying to help run our own site, our own service that we provide to customers. So this is one log statement. And what a log is going to kind of give you is the classic journalism 101, the 5 W's, right? When? The timestamp with a time zone. And the time zone is absolutely crucial because without it, you don't really know what time it was. Where? So this is kind of another basic piece of information. What machine, what module or service of code, where in the code was it? Who? So this is also kind of interesting. In lots of systems, you really don't want, you almost want nothing to be happening outside of any authentication context. So usually you have what user or system user or something like that is this running under the permissions of. You don't really want too much happening in a permissionless void. Okay, what? So this is the log level, kind of the classic info warn error, as well as a bunch of key value pair information. So this is usually some kind of verb. Here's what I'm doing. Here's a bunch of information about it. So this is 4 W's, and the last one is what's missing. So why? Why is this happening? What is the context? What's really going on? And this kind of information is not usually easily extracted from a single log message in isolation. So to get that, you kind of have to sort of traverse the stack. So any modern kind of IT infrastructure is going to have lots of pieces that sort of sit on top of each other or talk to each other or do all these things. And they're all generating their own log messages. And something that you're really interested in is often going to traverse a lot of layers of this hierarchy. So to really learn why something is happening, you have to kind of examine multiple logs. You have to make a hypothesis, try to test it, try to figure out what's going on. This is the hard work, this is the heavy lifting, and this is really where the human kind of comes in. And this is what we want to kind of try to help out with the machine learning techniques. And so in this situation, you have at the way top of your stack some kind of application problem, and way down on the bottom, somebody changed the network firewall rule or something and caused your database running in VMware to not be able to talk to your middleware, and all the way up until the user actually gets the resource not found problem. So this is really tricky, this is really hard to figure out, and you've really got to bring all your tools to bear on this kind of a problem. All right, so why even bother? Why are we doing any of this? What do we get out of machine log data? And there's a few business justifications and use cases, but they all kind of revolve around this idea of enhanced visibility and organizational perception into your machines. So you, maybe for compliance reasons, you want to know that you're meeting your service level agreements, that you're operationally sound. Maybe you need to prove that you're deleting customer data after 30 days, or there's security reasons. You just want to know what's happening inside your architecture, inside your business. The IT infrastructure is the nervous system of your business, and these logs give you that visibility into it. And then, obviously, if stuff goes down, you need to know why. And there's also kind of business insights, like the urban legend of, or maybe even true story, I'm not totally sure, but Amazon did this testing and found that every 100 milliseconds slower the site loaded cost them X percentage of sales or something like this. So that's another kind of direction to take this. So what are the challenges? What makes this really difficult? And this Office Space kind of clip art guy who's very unhappy is going to be kind of my guidepost whenever I'm trying to show you a pain point or a problem or something that's really difficult about log data. And the first one that you would notice as soon as you start looking at your logs is there can be wildly varying formats. It's a lot like the old joke about the great thing about standards is there's so many to choose from. The log data kind of occupies this really interesting twilight netherworld between structured and unstructured data. Because it has structure, certainly. You look at any log statement, there's clearly something going on there. But the structure is not very nice, often, if you're looking at all of your logs in their entirety. or it's not very consistent, or it can vary from place to place. So this is really tricky. Logs can also be very specialized. So I'm not sure how many people in this room right now could say off the top of their head, what is this log, right? What is this? What does it mean? What's going on? It's a VMware log, but I only know that because I put it there. Can be really hard to look at logging statements without the specialized knowledge and really understand what's going on. Your systems can be very noisy, and until you really dig into the log data, you might not realize how much is going on, the rich interior life of your software. And you can also have these kind of cascading failures where, just like in the tech stack example, you can actually have basically the distributed systems version of that, where stuff that's happening on one system somewhere in your infrastructure is causing misbehavior elsewhere in a totally different machine, and you need to kind of follow it across the chain there. So this could be a really, really big challenge. So one last kind of tidbit to kind of contextualize log data is some other people within Sumo Logic always kind of like to make this sort of jokey analogy that logs are like machine tweets. They're sort of these brief status updates or things being brought to your attention by your pieces of software. It's, hey, maybe you'd be interested in this. Hey, I'm doing that right now. But to carry that analogy, the comparison just a little further, Twitter had a really interesting blog post last year about their peak record ever for tweets per second. And it was coming out of basically Japan, where they were watching. There was a television screening of a Hayao Miyazaki film where apparently there's something that everybody tweets about in that movie. And so they hit the burst record for all time, probably. Maybe they've surpassed it now. One thing that was interesting in that blog post is they said that the kind of base rate average is 6,000 tweets per second. So like I said, I'm not going to go too much into these numbers and try to bludgeon you with them. But just for context, if you're generating 1 terabyte per day of log data, which is totally plausible for a wide variety of organizations, doing a little bit, making a few assumptions, and doing some back-of-the-envelope arithmetic, this is about 25,000 log messages per second. So, again, this is super kind of tongue-in-cheek comparison, but it's like 4 Twitters, right, in one company just from your logs. So I'm not going to use the B word with my data here, but scale concerns do come into play. This can be challenging. So the context for all of this analysis and machine learning stuff we'll be talking about is that it could be happening against the backdrop of this kind of scale. And again, kind of back off from this a little bit. I'm not making that exact comparison. Twitter probably does tons of other stuff that we don't necessarily do with logs, and we don't embed ads in your log stream yet. I've suggested it, but I don't know if we're going to go that way. So it's not a perfect comparison, but just to kind of give you a ballpark feel for what's a realistic situation. So machine learning. Now this part. So kind of a very sort of rough, simple explanation. Machine learning is about systems that learn from experience, that can improve with exposure to data. And there's a wide variety of flavors. There's supervised learning, unsupervised learning, all of these different things, algorithms for solving it, all kinds of stuff like that. So again, what I'm going to really be focusing on in this talk is defining crisp, nice machine learning problems. And kind of the template for the rest of this is I'm going to say, here's a classic kind of machine learning problem that's people know about it, people know how to solve it. Any machine learning practitioner, if you brought this to them, they would say, yes, that. There's chapters and textbooks about them. I'm going to give you the problem, show you a log problem, and then show you how you can connect the two and phrase your log problem as a nice machine learning problem. So let's get started with that. This symbol, this kind of, it's basically a common math way to say I'm estimating a function. So just like that pain point guy was to call out that we're talking about something that's really a big challenge, this symbol is kind of, here's a machine learning problem boiled down to this given do format, which I kind of picked up from my PhD advisor, who picked up from his PhD advisor, and it's just a nice way to really crisply think about your machine learning problem. It's sort of the first step. Given what data, what am I trying to learn, what am I trying to do? And so one classic machine learning problem is unsupervised clustering. So given some set of items, we'd like to group the similar ones. And this is a really schematic example where we have these points on a plane, and let's say we throw any one of many, many possible unsupervised clustering algorithms at it, we get this nice breakdown. Okay, great. That's unsupervised clustering. That's what an unsupervised clustering problem and solution look like. So what's the log problem? What's this office guy very unhappy about? It's too many logs and data disorientation. So once you have the tooling to collect all of your logs, it can actually be rather overwhelming. So this is from 30 minutes of activity of one of our testing systems, one component. 60,000 logs, 4,000 pages. This is already out of human comprehension. This is beyond human scale. We're just dead in the water. And what we can do is we want to drill down and distill them to the underlying structure. Log data can be really repetitive and kind of have this printf flavor. And so we can group log messages by their printf and get this kind of template wildcard representation. And so the feature that does this in Sumo Logic is called log reduce, and sort of, again, playing a little loose, it kind of compresses your results 1,000 times in this case, where now we only have 2 pages. And you get this kind of printf story. So a lot of log data is ultimately generated by printf somewhere in your code. So there's a template which is fixed, and then some variable positions which are different in every different execution of this printf statement. And as your program runs, it generates log data. So this one is some health status check, and you can see that zim and dib are fine, but GER2 is timed out, okay. These are the templates. This is the log data, and we'd like to magically, using machine learning, go from the observed output in your logging statements back to the printf which created them. Okay, so now bring it right back to unsupervised clustering. So now, given log messages, group by signature. And so signature is what I'm going to be saying is kind of printf. The printf is the signature, and you can kind of partition the logs by the generating printf. So how would you do this? Well, you can define like a string distance function. In this case, it's Levenstein, and this is kind of an edit distance. How far apart are these 2 strings? Well, we have to make 2 edits to make them identical, so it's distance 2. And then you can kind of think through and wave your hands a little bit and say, map this kind of notion of distance to this balls in the plane scenario. And so that's a way in which we are able to group similar logs together and get these printf level view. So this is a lot easier to wrap your head around, from 4,000 pages down to 2 pages. Furthermore, from this printf view, we're going to let you actually drill back into the raw logs. And this is the opposite of the sad guy. This is the happy guy. And I'm going to use this to kind of try to call out situations where I think there's like a really important general principle of what is useful in these kind of systems, what users find intuitive and useful. And here the example is that even if we're going to do fancy this clustering thing, get the printf with the wildcards, the user needs to be able to get back to the raw data really easily, because they might not, your clustering might be off, they might want to see what was the data underlying this thing that you did, all of these reasons. So whatever fancy analysis you do in this kind of tooling, in a machine data context, in a machine learning product context, you really want to give people a way to get back to the raw data. So partially supervised clustering. This is kind of a twist on unsupervised clustering, where you have similar items plus side information. So in this case, there's a link between these 2 points where we're going to say that we know they should belong to the same cluster. And now when we cluster them, we end up with this different solution because of this side information. And the situation here is that we've kind of injected a little bit more human expertise into the purely automated, unsupervised clustering algorithm. And we can see where this is going to come in handy for the log data case is maybe we do this clustering on logs and there's too many wildcards. We've over-clustered things. So the guy's not happy with those results. So there's a hook in this feature in Sumo Logic where you can just say, okay, that clustering is not quite right, break it apart. And now we've broken it apart into 2 different clusters with a little finer granularity. And obviously you can end up in the opposite situation where there's not enough wildcards. We've left something ungrouped that should have been grouped. And likewise, you can kind of edit that and say, okay, tell the clustering algorithm that you want to go back and modify the results a little bit. So another kind of classic machine learning problem that anybody who's used a modern search engine is aware of is this learning to rank. So given some set of items and given some history, we want to rank things by relevance. So this is a Bing search for data mining. And using whatever they're using under the hood, they've ranked the results this way. So this is a way for search engines to kind of boil down the vast number of possible web pages and rank them for you and just kind of give you those top results. So the pain point here with log data might be that 2 pages is still too many. People can be really busy. People are under the gun trying to figure stuff out really quickly about why their site might be having operational problems. So what we can do here is we can turn that into a learning to rank situation. So in this case, we have all these logs. Some of them are very similar in their content. They have database in them. And if the user wants to say, okay, this one is really interesting, they can explicitly say so, or they could, just by us monitoring how they interact with the results, we could kind of learn that a given user, they're really focused on database results. And we could be, so after, this is on top of the clustering, now we're going to present them with a ranked list of the clusters in terms of what we're guessing the relevance is for them. So this is also kind of another way to really sort of bring this inhuman flood of 4,000 pages of log data down to this cluster scale where it's something humans can look at and then rank it so you can see the results really easily. And so this is a true story of some case where this was used to troubleshoot at a digital media company. And it's kind of the classic site is acting weird. So maybe some KPIs are off, something like this. And investigating with the log reduce feature, basically, instead of you don't even know where to start, you can just kind of throw all of the potentially implicated components through this clustering machinery. And when done, it just turned out that there was a very obvious pop right to the top smoking gun of basically a problem with the latest code deploy in the content publishing workflow. And so this was really kind of an obvious giveaway that would have been really hard to find out by just manually dredging through logs or unless you knew what to look for. So by just kind of giving you this human scale, top level bird's eye view, it's a lot easier to figure out what's going on. And once there's that message, it could kind of be, you could also see another error associated with, okay, the consequence of this later in the production user-facing service, objects are missing because of this other bug in basically the publishing workflow. And so this, it kind of gives you the ability to skim your log data by using this clustering. And maybe you create an alert on it or something like that. So there are all sorts of other fun kind of true stories where people in different domains were able to use this to really do mean time to investigation or identification, rather, take it down from hours to minutes. Instead of having no idea where to start, you just look at the clusters. Or in a security case, you can kind of look at the signatures. Does something really weird bubble up to the top? Is that something, a signature, a printf, I've never seen before? What's going on with that? So just from customers have found this really useful in a lot of conversations with them, and it's a very popular kind of feature. So the general lessons, again, I think this is all great, and the product is wonderful, and la, 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 but I'd really like to try to abstract from that a little bit and kind of boil down some takeaways for building systems that explore machine data and systems that leverage machine learning. And these are things that we've kind of learned in conversations with users, people kind of discussions with UX folks, and even other talks or conversations at Strata, past and present. So you really need to combat data disorientation. In any kind of system that gives you access to a huge amount of data, which is going to often be the case in a machine data context, it's very easy to be totally disoriented and have no idea where to even dig in. And kind of an analogous talk was the, as some past years, some folks from LinkedIn, maybe, I think it was DJ Patil, but it's sort of people you may know at LinkedIn kind of tries to help you get oriented within their system. You first sign up and you don't know anybody and what's going on, and they're going to try to suggest some people at you to help you kind of get your feet wet and see the lay of the land. So surface latent structure. So a lot of data, even if it's not nicely structured, it might have this sort of latent structure in the data itself that could be unearthed by these kind of unsupervised techniques. So there's clustering and, again, sort of a little more machine learning-y, but there's dimensionality reduction, there's PCA, SVD, all of these kind of things where you can say, okay, if there is statistical regularity in the data, instead of just presenting the user sort of a raw dump of the data, we can try to learn the statistical regularities in it and show them that to kind of give them a distilled view. Anytime you do this kind of fancy stuff, though, you really still want to give the user an out to get back to the raw data. Maybe they're not as enamored of your fancy abstractions as you are, or maybe they don't trust the result unless they can kind of really see for themselves the actual individual items. So just from a confidence building and usability perspective, having those hooks where it's seamless to get back to the raw data is really important. And finally, it's really nice to empower the users to improve the results. And here, kind of an instant gratification timescale is really ideal. So if they, again, when we showed those kind of clusters, unsupervised clustering is hard. Maybe there are some mistakes. We'd like to give the user really easy hooks to be able to tweak and improve the results, and then they would benefit from that next time because the system will remember their results. So this is another kind of efficacy thing where if users, if they're going to get a benefit from it, they're going to be willing to click a thing here or there and kind of improve the results for themselves. So that's the first kind of stage. So the next step is, in the security case, we were talking about log reduce. Maybe you want to look for something unusual. And now we've been really lately working on a new feature that basically takes that one step further, where we're going to be looking for the famous, much discussed unknown unknowns. And this is kind of an outlier detection story. And so if any of you were lucky enough to catch Ted Dunning's talk Tuesday, I'm going to be, for almost the rest of this talk, I'm going to say if you saw Ted Dunning's talk, there's some stuff here, there's some overlap. There was a really good and interesting overview of anomaly detection stuff, and I really recommend it. But if you haven't, or even if you have and you want another refresher, outlier detection is another kind of nice, well, maybe not as nice, but very well-studied machine learning problem, where you have a collection of data and you want to identify outliers, stuff that doesn't seem like it fits. It's the classic Sesame Street, one of these things is not like the other story. And again, from the human perspective, we can kind of look at this schematic version and say, that guy's the outlier. So what's the log data version of this? And we can turn the log data into an anomaly detection problem using log reduce. So given your stream of log data, we'd like to flag anomalous points in time. And here we have three kind of example printfs, three example signatures, along with their counts at times 1, 2, 3. So we're seeing these printfs, we've grouped them together, and we're seeing these counts over time. Okay, well, what's going on at T3? All of a sudden, all your transactions are timing out and being retried, and something crazy is happening. So what we'd like to do is bring that to your attention. So in the particular feature, as it's implemented in Sumo Logic, there's kind of a timeline view, and you can click. We'll bring this to your attention and say, something weird is happening here. Now, if you click on it, you're going to be taken to this page where you're going to get to investigate and kind of annotate. And this is sort of similar to before the log reduce results, where we're giving you the signatures, the printfs, and as well as the logs, the raw data. So again, there's kind of this continuum of abstraction and scale between raw data, logs, millions per day, overwhelming, and kind of human scale, something that you or I can relate to and tell each other about and understand at that granularity. So here we have the logs, and that's kind of how I'd like you to think about the signature printf clustering stuff, kind of introducing an abstraction layer on top of the raw data by exploiting the underlying structure. So this is what we show you. And then you also get to see, basically associated with each signature, an explanation of why it was included in this result. Here in this page, we're telling you why this period of time was so unusual. And we're trying to score the individual signatures. This one has gone way up and way out of whack. This is why we've brought it to your attention. So then, let's say that you look at the signature and you say, as a human user, I want to annotate what's going on here. So the signature this printf is way up. It means database timeouts. You can mark it up, and now basically, with your help as the user, we've introduced another layer of abstraction. So you have raw logs, you cluster the logs, and then we look at patterns of deviation in those clusters, and the user can kind of tag them. So if this printf goes way up, the user says, it's database timeout. And now we've created kind of another synthetic layer of abstraction closer to the human scale. And this is kind of the event, is what we're going to call it. And then kind of not to tip my hand, but then we want to go up even one further than that later to say, we want these events on the timeline. We want to alert you about them and that sort of thing. Now, how that could happen is this supervised classification regime. So this is kind of the classic machine learning. If you have to explain machine learning to somebody out of the field on the street, you say, spam versus no spam, right? Hillary Mason has a really cool tutorial that you can kind of work through and kind of a classic thing. And everybody can kind of wrap their head around, I want to teach the computer to tell A's from B's, to tell spams from no spams. And in this situation, you have the red dots and the blue dots, and you can kind of draw this nice line, and you're either on one side of it or the other. Okay, so supervised classification is sort of the granddaddy of them all in these machine learning problems. Very well studied. How can we use it? Given the log data and the annotated events, we will classify new occurrences as belonging to the annotated events or not. And so now we've really taken it up the stack of abstraction here. So way back when, earlier in this talk, I showed you the unhappy man looking at 4,000 pages of log data. What are you going to do with that? He's overwhelmed. And now, at this way other extreme of the abstraction hierarchy, we're in a situation where we have a nice timeline of annotated events at the human scale, explainable to even a manager, right? So this is really, how did we get here, is by kind of one piece at a time, trying to build up layers of abstraction with machine learning techniques and with user participation. So really, to kind of get the most out of your roughly structured data in the machine data arena, it really seems like a killer combination to merge machine learning techniques with this human feedback and expertise. And you get this kind of nice annotated semantic timeline. And really sort of, this is a little bit more like vision than where we're at right now, but ultimately, this feature is basically using machine learning to bootstrap the creation of a fingerprint database of machine behaviors, right? And so this is kind of where we'd like to be going. It would basically give you this scenario where you plug in, you start sending some log data into the system, and we're able to say, boom, your MySQL is hacked, your Apache's misconfigured, this kind of thing. And what makes this possible is by this kind of machine learning pipeline that we can be constructed. And so the kind of stuff that this feature has sort of already been catching in sort of limited customer trials and everything like that is SSH problems, configurations, potential security events, various misconfigurations, things like this. So there's really some interesting things you can find just by trawling through the logs with this kind of technology. So again, kind of let's step back a second and say, okay, what are the general lessons for machine data processing, for machine learning-enabled product features? You really want to explain your algorithm's decisions, at least somewhat. Maybe you don't need to show them the SVM hyperparameters you used or something like this, some incredibly esoteric technical version, but some really comprehensible, simple thing where you just say, the machine is making this guess because X. So Netflix has this really nice stuff with their recommendations now where they sort of say, we think you'll like this movie because you like that one. This kind of thing is really useful. Again, you really want to link to the underlying data. No matter how nice your machine learning or your pipeline or your fancy analysis, users are going to want to see it for themselves. They're going to want to dig in. And again, users will, if they're getting benefit from it, they will appreciate the chance to kind of be empowered to improve the results, to improve the system. And if you can harness that to really, really build something interesting, that's a great win too. So that's the big stuff. I guess real quick, I'll just say one more thing is we're doing some interesting stuff with time series. So this is not in Sumo Logic. This is the Python stack. So there's been some great speakers and people at this conference from that scientific Python world. But basically, you have a lot of the same problems with time series data. We parse out fields from the logs, and now we have these issues where it's really noisy, it's really messy. And so there's a whole world of techniques from machine learning and signal processing where, given time series data, we want to break it down into pieces. And again, not to repeat, but okay, the Ted Dunning talk, you talked a lot about time series data and a lot about decomposing it. And here we have a situation where you have really messy data, and now maybe we can show you something a lot cleaner by applying, in this case, it was a Hodrick-Prescott filter. And again, also time series, anomaly detection. Maybe you want to be able to say, this is an internal component at Sumo Logic, and these two spikes correspond to when it was restarted and basically had to burn down its backlog queue. So this is how much data it's sending, and there's two huge spikes because it was shut down and restarted. And in an operations context or something like that, this may be something you'd be really interested in. So how you can do that is maybe with a windowed model, and just very quickly, very simply, maybe standard 3 sigma deviation or something. This is in the product. This is something you can do. There's fancier things you can do. There's all sorts of stuff to be done here, and this is kind of future interesting thing. But a lot of the same lessons from the earlier work apply. You can use this financial services, security, operations. It's just a very general problem. But again, I would say these same ideas. Tie it to the raw data, extract latent structure, give the user hooks and feedback. It's basically very similar. Again, so also I would highly advise be aware of the literature, right? Machine data is kind of people have been applying stuff to it, but it's still sort of open. There's still interesting stuff to be done, but it really helps if you can kind of go through the related literature and find some interesting stuff there. All right, so this is it. I got to close with the obligatory plugs. There's a free sumo.com trial where you can go play with the service if you like. We have a booth in the thing, and we are, of course, hiring, so feel free to talk to me. So I have a few minutes for questions. Can you go to the mic? Maybe it's not.
All right. Yeah. So to this machine classification apparatus, is it possible to configure what stream of data you want to send? Because typically what you want to do is it's just a distributed problem where you get logs from multiple machines and you want to go plus minus 1 minute of some particular time. That's what I want to send in to this classification apparatus machine and see what kind of patterns it detects.
That's right.
So and does that happen in real time, or like you just send it and something has to crunch through it, and there's a time delay between when you send the feed to when you get the analysis?
Okay, great. So this is a little more kind of like detail about how it's implemented in the product. But yeah, it is real-time streaming data processing. So, and it is also the feeds are kind of configurable. So you would have separate reports that you basically write like a query or filter and say, my logs from front-end nodes, they all go together, feed them through the classification tech. My logs from database, feed them through the classification tech. So you'd actually, I showed you timelines with this nice annotation. Actually, in the product, you would have separate timelines that you sort of create one for each thing. And then these timelines are kind of powered by like real-time streaming data. So this is kind of bonus slide that I didn't really get into. But yeah, the architecture is this kind of scale-out streaming thing.
I'm curious about your supervised learning on log data. I've never done that. So my question is pretty, from a neophyte perspective, I guess. What do you use as labels? Do you use an existing field in the log data, or do you have to manually go in and create this labeled data?
Sure. So what are the labels when you're trying to do supervised learning on log data? So here, in this particular feature, the granularity is not so much the individual logs, but the collection of logs from a point in time. So what we're classifying is the set of logs from point of time X. And the features here are basically roughly is sort of what printfs are we seeing at that point in time. So the clustering, the unsupervised learning, actually provides the features for that point in time. And then the labeling is essentially done by the users when they annotate an event. So when the user annotates an event, they are labeling it, okay, database failure. So that's where the labels come from, and that's kind of what the features are in this context. Although there's lots of so many opportunities for applying this kind of stuff to log data.
Hi, I'm working similar stuff. So my question is about, like, those logs are pretty messy, and if you want to catch in a very short moment, like the log can be like in a few minute time frame. And so is the classification or clustering question that we are dealing with could be classifying like millions or even more records or terabytes of data. So how could you deal with that and in a current framework? Even you have like Hadoop or parallels things, but it's just very hard to classify clusters, these big data, especially they're pretty messy. So can you share more details?
Sure. So in this situation, again, kind of the clustering, it's an interesting thing. I guess what I would say at a high level is that for a lot of machine learning algorithms, you can have a situation where training is expensive, but testing is cheap, right? So, for example, not to say that we're using deep learning or whatever, but there have been a lot of talks about it. That's a situation where training a deep learning model is this monstrous Google scale thing that takes Jeff Dean and 8 million CPUs or whatever. But testing or evaluating or predicting from a deep learning net is so cheap you can do it on your phone, right? And so that's kind of speech recognition in your phone these days. Incredibly expensive training, very easy, very fast prediction. And so that's kind of a property that can be leveraged with log data too.
So when you get data and logs from different sources, so if you have, say, several different systems running, how do you take those sources and extract them across, or run similar types of extractions across those different sources, and then combine that into something that actually goes into your model?
Sure. So there's, like I said, this kind of falls almost into sort of sumo logic deep dive, where there's a lot of kind of configuration that can be done when you're setting up the sources that feed into the cloud system. So at that time, you could kind of tag your sources and say, okay, this is front-end node or not. Or even if you don't do it at that time, later that could be parsed out if it's in a text field in the log. So we could kind of do it later. Right now, or even, it's not hard to imagine that could be a machine learning problem too, right? But at the moment, it's kind of a configuration problem, ultimately, where you want to, when you're setting up the ingest pipeline, when you're sending the logs in the first place, there's kind of some metadata that goes along with those requests that says it's customer XYZ, source ABC, and so on and so forth. So for now, kind of configuration. Or we could talk offline after if that doesn't quite answer.
Hi. So when you have, there are like tens and thousands of machines running, and these machines are basically sending you real-time logs, and you're dependent on all these machines, and then there are always maybe like 2%, 1% of the machines that are not sending the logs at the right time. And like, how do you handle such situations where you basically, I'm feeding all the stuff, you're sort of correlating them, you're coming up with some kind of analysis telling me here is what's going on, but there is this late arriving data which should have come earlier but is coming late. How do you handle such scenarios?
Sure. So depends on what kind of analysis you're doing. In the general product, there's sort of a notion where it kind of gets backfilled a little bit. So it would, the system would incorporate that if you're just doing kind of a standard like SQL style aggregate query. For the anomaly detection stuff, that might actually be a kind of anomaly, and maybe it's something you would want to know about, right? So actually, if I'm not getting data, that's also something that can happen and might be flagged as server missing, right? No data coming in. And maybe it's just because it's late or it's delayed, but maybe it's because it's actually down and gone. And in that case, that's an anomaly you would want to know about. So that's my kind of answer, I guess. I hope that makes sense.
Do you have office hours today?
So I'll be hanging around either this track or the Sumo Logic booth.
All right, I'm very interested in, can you give us pointers to further reading for analyzing time series, like anomaly detection or whatever predictive things you can do? I mean, I'm aware that you can decompose time series into various components, but not much more than that.
Oh, sure. So what I can do is two things. Is I could post like a comment on the talk page on Strata webpage. So there's kind of a page for the talk. I'll put a comment there. And then likewise, fish out Ted Dunning's talk. I guess I sent another plug for that one. Cool. All right. Well, thank you all for listening. Now we have another talk.